move into the section. So what we've done so far then in terms of competition is we've tried to get a sense of what are some of the factors that are competed for. Okay? And we talk about nutrients, water being particularly important, light being important. Okay? So I'll see how many, 2 of these methods are really important. I mean, 3 are commonly used. I wouldn't say they're important. And I'm hoping to get through these today. And 2 others that I list is just more informational for you. I won't probably get to them, but I just wanted you to be aware of them. Okay? The first one that we're going to look at is called the critical period of interference / competition. Remember, interference is the broader term that encompasses both competition and allelopathy. So when somebody talks about, you know, I'm going to be studying, you know, crop-weed interactions or interference, there's a possibility that allelopathy is playing a role there. So that's why I've put both. But this is going to be an important concept. Hopefully, some of you might actually, you know, try some of this in some of your, if you're doing an undergraduate project or even, you know, a work in your you know, work study. That's going to be important. Second, and I'll talk more about each of these, is referred to as the additive design or weed threshold studies, where basically we're trying to figure out, you know, what is the relationship of crop yield to density of a weed? Okay? So if I have 2 velvet leaf plants per foot row of corn, what is going to be my yield loss if the crop stays in there or the weed stays in there full season? Or what about if I only have 1 velvet leaf plant? What about if I have 100 velvet leaf plants per foot row or per square meter? That is, we're trying to get that relationship. Where, when, at what density should a grower be concerned? So if remember in IPM we talk about, you know, economic entry level thresholds. This is what this design allows you to do. And I'll tell you a bit about how this is set up. This is by far the more realistic design. It's very closely parallels the reality out there of what growers typically are doing. And I'll mention a few things about it. The more, I wouldn't say theoretical, but one that's the substitutive approach, also referred to as the replacement series design, okay, is one that's more commonly used in research, where you're trying to get a feel for, I wonder which species is more competitive. This weed, velvet leaf, or red root pigweed, or corn, okay? You're trying to get a hierarchy of competitive abilities. And I'll show you this method. And in fact, I use this method, okay, for my PhD work. So it is used, where I was trying to figure out what was the impact of a fungal pathogen on the competitive interactions between velvet leaf and soybean. Okay? And I wanted to see, did it shift the competitive, having this pathogen there that attacked the velvet leaf, did it shift the competitive balance? Okay? And I'll show you how that's done. That's one that a lot of, actually I've had a number of undergraduate students who are doing independent research projects use this approach. So as we go through it, you might say, this is something I may want to use. The neighborhood model I won't spend much time on. I just want you to be aware that it's there. What this model does, okay, and you'll have it in your notes, is really trying to take, remember I told you that, and here's a question, you know, that might come up in the prelim. Very quick answer. What's more important, okay? Time of emergence or proximity to the crop in terms of weeds causing more damage or greater yield loss? Emergence timing is much more important. When you emerge, if you emerge before at the same time as your crop, that's when you're likely to have the greatest impact, negative impact. Okay? What this model does is not only takes into account emergence, but also distance of your weed. So it's very tedious. A lot of data has to be collected. And you can then create what's called a regression curve to figure out, well, obviously a weed that's closest to the crop is going to cause more injury or greater yield loss than a weed that's 10 feet away. Okay? So that's what the neighborhood model is. But it's, and again, I'm not going to spend much time on it since it is used, but it's not the most common of the methods. And the last one, for those who are interested in intercropping studies, referred to as the systematic design. I'm not going to say much here because when we get to cultural control, I'll talk a little bit about intercropping and I'll bring some of this up. Okay? So the methods that we're going to focus on this morning are the critical period of interference, additive design, which is very realistic. Okay? So is this one actually. And the substitutive approach or replacement series design. These are synonyms. You might see both terms used or one of the other, but they mean the same thing. That's more of a research type approach. Okay? So, critical period of weed competition. Why is that going to be important? What is that? That's one of the things you need to think about is that, and you remember this? Do you remember this little thing, the little design? If I were to show you this on the prelim, and just put that up there and say, tell me what this is about. What important principle is being addressed here, or at least explored? What would you say? I would just have this there, and you say, I would have said, you have seen this in class. What is this referring to? I hope you're able to say something like, this indicates the ability of species that emerge, or it indicates, or at least shows that species or seeds that germinate or emerge first, those individuals tend to occupy more space, i.e. grow the most and be most competitive. Okay? Their area of influence is much greater than the others. What I'm saying, the reason I put this back up here is there a time period during when weeds really compete with the crop? Early on in the season, okay, if this was say the crop was right back here, these guys are so small that you're likely not to have competition occurring at this stage for nutrients, water. They're just too small, okay? So individual plants are too far apart to be competing for the same resource. I mean, this is generally true. Early on, yeah, you could wait a few days or a week. You're not going to lose 50% yield. But what happens is, as plants, the weeds become larger, so as well as your crop, but the weeds particularly, they will start suppressing, okay, the crop and other weeds. So what I'm getting at is, what is that period? How long can these weeds remain with your crop early on? Remember we talked about that? There are two scenarios. A grower can wait, and that's what we do when we're applying Roundup Ready crop. In Roundup Ready systems, what are we doing? We're waiting, we're allowing the weeds to germinate, to emerge, and the grower waits up to a given stage where they're already told this work has been done. Say, well, yeah, if you wait past the V5 stage of corn, or past the second trifoliate leaf of soybean, you're going to be in trouble if the weeds are competing. So the question is, what is that period? How long can a grower wait, allow the weeds to stay in with the crop before they'll get a major yield reduction? Remember, for most growers, a 5% yield reduction is the max that often they can handle, 5 or 10% at the most, okay, from a weed-free crop. So that's the question. That's critically important, okay? So here's the various scenarios, and you do have this figure, okay? So the other situation is where the grower is not going to allow, okay, any weeds in their crop early on. I mean, ideally, if the grower doesn't allow any weeds throughout the growing season, that's, well, clearly there are no weeds, but that's costly. You've got to put down residual herbicides. It's not always easy. So the situation might be that here's the crop. This is scenario A. You've got weeds. There's no weeds. The grower has done a great job. They've used pre-emergent herbicide, or they've tilled, they rotor, they may flame weeded, you name it. But then the question they have, so this is that period. So let's say you're growing, sugar beets, or you're growing onions or corn. The question then is, how long does the grower have to keep their land or their field free of weeds, such that if weeds come back, and of course weeds are germinating at different times, as you saw, they're not all coming up in May, although a good number of them do. You will have them coming up throughout. The question is, how long does the grower have to wait? How many weeks? At what growth stage? Such that weeds that emerge afterwards are not going to cause significant yield reductions, i.e. more than 5%. Okay? So that's, okay, this is what this is. And so that would be something where you're basically going to, and I actually, what I would have done, I realized that I moved this in the Bronx section. So this here, the critical weed-free requirement should be up here. Okay? So this, okay, you don't have it in your notes, but I just included it here, but I realized I put it in the wrong spot. It should be right up here. Basically, what is the critical weed-free requirement? How long does your crop have to be weed-free such that if weeds come in afterwards, it's not going to cause a main, okay? And that is Roman numeral 2. That's one scenario. The second scenario, which also happens, it's very common, is that you allow your weeds to be in with your crop for a given period of time. Okay? And this period is indicated by Roman numeral 1. So let's say the grower doesn't get in or is using Roundup, okay, in Roundup-ready crops. So that herbicide can be applied post-emergent. In fact, it's only applied post-emergent. Okay? So the grower's going to allow the weeds to come up, but they need to be aware of, you know, how long can the weeds stay in there without then causing significant yield losses. Okay? So this is then referred to as, then, this is correct, the critical duration of weed competition. Okay? This period 1. When you combine period 1 and period 2, this one up here, you get this overlap. This is referred to as the critical period of weed control. Okay? That is the window, and it could be based on number of weeks since planting, but more commonly what's used is crop stage because of weather, right? Weather can, you know, one year it could be cool and you can't say, well, it's going to be 4 weeks and think that every year it's going to be 4 weeks when you have to apply your treatment, whether it's cultivation or herbicide. So the best indicator is growing degree days might be a good way to do it, or, you know, closely related is plant growth stage of your crop. So V3 stage, V5, i.e., when corn gets to the V5 stage, I need to do something. Otherwise, I'm going to get yield reductions. Or I can keep my field weed-free till the V5 stage. Afterwards, if weeds come into my field, given the competitiveness of the crop and field conditions, that shouldn't cause a yield reduction. Okay? That is, again, the critical weed-free or the critical period of weed control. That's when you've got to get in there. This is extremely practical, and it's been done for many crops. This, okay, these periods then depend on a couple of things. What do you think is going to drive how wide that window is? How, okay, long this period is? So, you know, a weed-free period, what's going to drive it? What's going to be an important factor that's going to influence how long that period is going to be? Is it going to be 1 week? Do I have to keep my field 1 week weed-free and then the crop can take over? Or, my God, I've got to keep it 2 months?
It will depend on how vigorous the crop is.
Yeah, the competitiveness of the crop. Okay? Certainly the weeds too, but the competitiveness of the crop. And for the, you know, the critical period of weed competition, how competitive the crop is, but particularly how competitive your weeds are. If you go very few wimpish weeds, but sometimes you do have certain weeds that are not as competitive in certain situations, okay? And so there, how competitive your weeds are, the kind of species you've got there, are they very aggressive type weeds, will give you an indication of how long your crop can tolerate, you know, having weeds present in. Yes, Megan?
But don't you also have to have some real understanding of like weather patterns and how they're going to affect it? Because every growing season, that threshold is going to be different.
Right. But what did I say that you could use to take into account? You may not do, you know, 3 weeks, but what could drive it? You know, what you could do is use growing degree days where you have an understanding and say when you reach, you know, 1,500 growing degree days, if, you know, or that you know, when the plants reach the V5 stage, if it took it 6 weeks to get there because it's been cool, or if it took 2 weeks because it was really warm in the spring, that you take into account. You say that's the stage where the crop can do it. So having some constant, absolutely, you're right, and it'll vary, but you know, by your field. Not everybody can. Even some of the numbers I'll show you, you might say under my field conditions back home on my farm, that doesn't happen. I mean, I can't just, you know, allow just 4 weeks of weed-free. I may need 6 weeks because of just the conditions. But generally speaking, that gives you an indication, okay, of when one needs. So the critical period of weed control is when you need to get in there, okay. Between what stages of the crop growth or growing degree days, whatever you want to use, you need to be aware of. Obviously, this is a disaster. You have a situation where your crop emerges and your weeds are in there and they're present throughout the growing season, 0. It's going to be 90% yield loss. And we have those, what we call our weedy checks. And you saw it in Stephanie's strut. I mean, you look at where's the crop. I mean, corn looks like a little, you know, there's no question. I don't think that's a non-issue. Okay, this is an important graph, okay? Because what we're going to do, what you do is, so how do you set up this experiment? You would basically set up this experiment you'd have two separate experiments. One experiment, so if you're trying to do this in your own fields, and now I've done it with growers. We do it in small parcels of land, or you can do it in a greenhouse, but also out here at Caldwell, is you set up a situation where you say you plant your corn. Let's say we're going to use corn. And you want to get an idea, how long does corn have to be weed-free such that there isn't going to be more than a 5% yield loss through the growing season. And what you do is, at all these intervals, 2 weeks, 4 weeks, 6 weeks, okay, or at the two-stage, V3, V4, you do it, you harvest the corn. And you look at, or not harvest the corn, you remove the weeds, or you keep, let's keep it weed-free for 2 weeks, weed-free for 3 weeks, 4 weeks, and you let the plant grow. Harvest time comes along, now you know the treatments. You look at your treatment, you harvest your corn, you look at yield when the weeds were allowed, or when the corn was weed-free for 2 weeks, weed-free for 3 weeks, 4 weeks, 5 weeks, and you get an idea of, oh, okay, so this is what this graph is going to show, okay? The solid line is the weed-free period. What they're looking at here is for sugar beets, but so what this is saying is, if you allow, okay, this crop to be weed-free for 2 weeks, so let's say we're in sugar beets, okay, and what you did is, at the beginning of the season, you plant your sugar beets, and you do all your best management, you keep weeds out of there for 2 weeks. And then if weeds come back in, you don't do a thing. Is that going to cause you a major yield reaction? The answer is absolutely. You harvest those sugar beets at the end of the growing season and look at what the relative yield to your control, i.e. weed-free for the whole growing season. You're only going to get 10% of your yield that you would have had if you had kept everything clean, which is what growers are aiming. Do you see what I'm getting at? So 2 weeks, okay, keeping the crop weed-free for 2 weeks is not going to give you, what you're looking for. You're going to suffer a 90% yield reduction, which is totally unacceptable, okay? So let's say you say, okay, 2 weeks is not enough. I'm going to allow 4 weeks of weed-free. I'm going to keep the weeds out of this crop for 4 weeks. Again, theoretical, under these conditions, okay? Look at what your yield is. 4 weeks, relative yield, relative to your weed-free is 40%. You're still losing 60% of your yield. And here the yield would be the marketable part, the root, okay? So that's non-acceptable, okay? 4 weeks in this crop is just not good enough. Let's go to 6 weeks. If we allow the crop to be weed-free for 6 weeks, what happens? We're about 70%, still not acceptable, okay? This is 5% yield loss, which is what I've told you is the acceptable level. That's up here, 95% relative yield, okay? So what I'm saying is even after 6 weeks, what is it telling you about this crop, sugar beets? What can you conclude already from looking at this? Sugar beet is not a very competitive crop under this scenario, okay? I'm not saying it's throughout, but that's true. Onions would look like that. So at what stage, how long then what is the wheat-free, minimum wheat-free requirement to get at least no more than a 5% yield loss? That's what this is, 10 weeks, okay, right there. See how this curve goes? You're at 10. You have to allow your crop to be weed-free for 10 weeks, such that if any weeds come in afterwards, you're not going to suffer more than a 5% yield loss, okay? So that's one component. What happens in the situation where you start out with the weeds? Remember I said the Roundup Ready situation, where the grower is going to allow the weeds because they know they're going to go and spray post-emergent once the weeds are up. The question is, how long can the weeds stay in such that they won't cause more than a 5% yield reduction? That is the diagonal or the dashed line, okay? So at 0 weeks, basically when you start, the weeds are in there. Okay, after 2 weeks, okay? So if you allow the weeds to grow in with the soybean, the sugar beets for 2 weeks, not bad, okay? You're gonna be at 95%. You'll suffer, you'll be at like a 97%. You may suffer a 2 or 3% yield. That's pretty good. What happens if you allow the weeds to be in there for 4 weeks? Now, the weeds are sitting with your crop. You go, oh, no problem. I couldn't get in because it rained. It's too wet to cultivate. That happens. And the only time you can get in is 4 weeks later, okay, from planting. Look at what happens, okay? 4 weeks, you're now, approximately here, okay? you're below the 5%. You have now suffered a major yield reduction. Okay? So what is the, the period, the critical period of competition in this case? Okay? How long can the weeds be allowed to be in this crop under these circumstances? Just between 3 and 4 weeks. Okay? 3 and 4 weeks is what the only amount of time that you could allow your crop to be in with your weeds. And again, you could see that this will vary by season. Okay? But instead of using weeks, you could say plant growth stage. V3, V1, whatever they use for sugar beets, 3 leaves, whatever growth stage. Or growing degree days, because that'll take into account if it's a warm spring, cool spring, and of course that's going to determine how well the plants and the weeds grow. But you get the idea? This overlap, this distance here between 3 and 10 weeks is then the critical period of weed control. It is between this period that a grower must get in to the field, do something, cultivate, if you're, an organic grower, flame weed, use a biocontrol agent, use herbicides. This is the period, okay? And that is the period, the critical period of weed control. So where these two overlap. Do you get the general gist of this? Okay? Now, you're going to say, well, I know growers that they're not going to allow any weed. They're going to be weed-free, okay? This weed-free period, they're not going to want to let anything come in. Fair enough. But if that's not the case, and it happens, or you don't want to use herbicides throughout the growing season, or you don't want to cultivate all the time, you're a person, you're a grower that tolerates a certain amount of weeds in there. We do have growers that's fine. So that's what we then try to calculate. Okay? This is used. Okay? It's used, and you'll see some in your handouts, in the notes. I give you examples of what each of these periods are for a combination of crops and weeds. Okay? I will not ask you, tell me what the critical weed-free period is for corn when it's growing with mixed weeds, including broadleaf weeds like redroot pigweed but get the general idea that will indicate how competitive a crop is and is not.
Now,
yes, Scott.
If you utilize, as a grower, if you utilize that window, are you also able to minimize the selection for resistance? Does that also correspond with minimizing?
Right. And that's one of an important mitigation of the development of herbicide resistance, because the grower is going to say, and that's why we have herbicides that have residual activity, i.e. they're active throughout the growing season. That's great. But what it's also causing, and we're seeing it, is development of herbicide resistance. Because basically that herbicide is active throughout the season, and you will, over time, have some individual weed species that will develop resistance to that. And the more they're in contact with that under selective pressure, okay, you're going to get resistance and you're going to get selection. So that's one, reason why we want to, try to use this. Organic growers use this a lot because they don't have residual herbicides to use. They need to be, timing is everything. Now, even for our conventional growers, timing is everything. They need to get in there and cultivate and if they don't do it at the right time, how many of you have been in situations, those of you that have been in farming, that basically you get into a field and you're seriously thinking you are going to suffer some major yield reductions? Anybody that's had anything to do with it knows that. For whatever reasons, the equipment didn't get there in time, you had a malfunction, you name it. And I've been with growers. You look at them and they always ask me, you say, do you think I'm going to, get hit here because of, getting in late or this new flush that I wasn't counting, or failure of my herbicide. Dry weather, pre-emergent herbicide doesn't work. Okay, or it's got, we got 3 inches of rain the day, 3 hours after we applied the herbicide. Everything got washed out. So these are real scenarios. These happen. This is not just theoretical. Okay? So what this is showing, and you don't have this, and that's why I wanted to include that in your handout. But what it's saying is basically, what is the optimal, the ideal stage? They're trying to control, using herbicides, they're trying to control grasses. And early on the grass, this is, basically 14 days after planting, okay? And if you would apply your herbicide when the plants are this big, what impact would that have on your yield? Okay? And should you be worried about foxtail at that stage? Okay? And so corn planted in early main fields with high natural foxtail pressure. Okay? And so what happens is you apply your treatment here, okay, and you get fairly good control, 53% control of the foxtails. Okay? You still get a bit of an 18% yield loss. Okay? Why? Why do you get an 18% yield loss? By treating at the 1-inch stage of the crop. Yeah, you're an eager grower. Yeah, I got to get out there, spray. Okay? And it's 2 weeks later, I'm spraying. The plants are this big, my foxtails.
Because it's so early that the foxtails, but they have time to grow back.
Exactly. You still have things emerging. That's not their peak emergence. And they're at 1 inch, they may not, so it's not that they're competing with the crop yet. They're not really at that stage. They're small enough and maybe far apart enough that's not. What this yield reduction is due to is the fact that you've got subsequent emergence of foxtails that are now not being controlled. Unless you have a residual herbicide, a herbicide that's active throughout. This is not the case here. Okay? You're applying post. Post means that you applied once the weeds are up. Okay? And we'll cover that. Okay, you say, well, I know that's the case. Things are going to be emerging. Let's wait 3 weeks. Okay? 77% control, a little better. You're still getting a yield reduction. Ideal timing, okay, for some of our post-emergence herbicides is when your grasses are 2 to 4 inches. Growers use that. Consultants use that. That's what they use. Because height and growth stage gives you a sense of how the season's gone. Okay? So if I tell you, this gives you an indication, okay? So you get 28 days after yield is your best yield. You still have 91% control. So the question is, hey, I don't have 100% control, but the crop is competitive enough at that stage that it's doing the job, okay? So what about this? Waiting till it's 4 to 6 inches. Why am I getting a yield reduction? Why am I getting a yield reduction? Here I'm getting, it's perfect. I'm getting my optimum, my maximum. I'm going 33 days later. I'm controlling 92% when I apply at this stage, and I'm getting a 6% yield reduction. Why? Competition. You've waited too long. These guys are, 4 to 6 inches, and again, it'll vary by crop. And certainly if you wait this long, till these guys are 7 to 9, let's say you didn't have a choice. It was wet. You couldn't get in. That's what happens. The equipment malfunctioned. The grower couldn't get, even our organic growers couldn't get in there. Guys are 7 to 10 inches. In this case, they're going to be applying a herbicide, so it wouldn't be our organic growers. But nonetheless, they may not get in with the equipment, or you have to readjust the equipment to get the right height so they don't go right over the crop and kill it. You're going to get, okay? So as you see, there is a optimal period that you need to be thinking. That gives you a good sense of, okay, the critical period, when you should do it. So this is another way that growers and consultants think about competition, when to put a treatment down, when to carry out a certain operation. You don't want to do it too early, knowing the weeds keep coming, particularly, And so this is a specific example here, but, okay, but yields are already reduced because of early season competition. That's really something to be thinking about. Okay? And the growers, the consultants are juggling this with the many other things that they need to be thinking about on a farm. Think about it, why it's become so specialized that, especially if you're a dairy person, you've got so many things thinking about just your herd and so forth, that this then becomes on top of that. You've got haying and you've got all other information. Okay? Again, this is something I just inserted because I found that, and you'll have a copy of this, but this is just showing the critical period of competition or of weed control. Okay? This is when you need to get in there, whatever that period is. We used to do this in this course. We used to do a lab. Okay? The manuscript that you have to write that I'll talk about in lab, by the way, Stephanie's research plots, I'll give you some information. We used to do that, a similar lab, this kind of experiment as your research project, your manuscript writing. And some years, you guys would plot these out, the students would plot, and they'd get nothing, okay? They just wouldn't have anything here, and they would say, what is there? I don't see that gap. What's going on, okay? What that was indicating is under the circumstances we used, we actually didn't have competition. There was, the weeds, okay? The weed-free period was very minimal. The weeds didn't impact the crop. Maybe the density wasn't high enough, but they didn't have this, okay? What this means is basically that there's no, although it's contrary to what we're all thinking, under our circumstances, again, density may not have been high, but it didn't impact yield, okay? Maybe there was enough fertility there, who knows? But what happened in our case, I know that our weed populations were not very high, and so we didn't get that. But in a couple of years, we got this, where basically you can keep this thing weed-free, okay, for 12 weeks, and you still don't get, the adequate yield. And so what this is saying, you better keep your, weeds emerging at any stage can result in yield loss, in more than 5%. So this is, when you get these situations, it's really bad. Usually this happens when you have a really poor competitor in terms of a crop. I see this in onions. I saw this in onions and particularly carrots. Very slow growing, and where weed control was a problem. Basically, the growers knew they had to keep their fields clean throughout the season. Otherwise, any weeds coming in would cause significant yield reductions. Okay? That's what this is. Look at this gap. I mean, it still hasn't reached its 90%. So this is pretty well saying you got to keep these things weed-free the whole season. And that's not a good thing. Okay? Now, that doesn't mean you have to, kill the weeds. What some of our organic growers know when they have these wheat, very poor competing crops, they'll put in mulch. They'll doing a whole bunch of different things to try to suppress the weeds. It's not like you throw your hands up and say, oh, the only thing that works is herbicides under this condition. No, that's not the case. You could use other strategies, but you have to be aware that you have to do them. You can't just rely on say, oh, if the weeds come in after, it's not a big deal. Throughout the season. Yes?
So you could wait till just before the critical period, but don't you want to control some weeds when they're small anyway? Because it's easier to control them before they get to a certain growth stage?
Right. And that's a couple of things that I'll talk about. That comes to. After having said this, there's going to be a couple of things that growers or in reality you need to think about. For organic growers in particular, but also our conventional growers, there's going to be a situation exactly what Megan says. We know that cultivation works best when we have seedlings that are really small. Okay? And you'll see this video that I'll show in lab where you see these vegetable growers when the guy says, when my pigweed is this size, what do you want to cultivate? I mean, you just turn it over, but this thing is going to reroot. Okay? And if you try to, there's a couple of ways you can kill weeds, right, with cultivation. What are they? One is, how do you kill weeds? You can uproot them, tear them, cut them. What else can you do? Just leave them on the surface. What else? Herbicides, but I'm thinking mechanical control by itself. Burial. You can bury things. There's, a couple of ways you could do it. And for perennials, what does continuous cultivation do?
Chopping up the rhizomes.
Right, and what does that result in? Deplete its resources and energy. That's what control can do. So and you'll see one of the growers will say it. I say, hey, there's a couple of ways my grandfather and father used to tell me you can kill weeds, particularly when they're small. You can bury them, you can tear them up, leave them on the surface and let them desiccate or dry out. And for perennials like Canada thistle and field bindweed, is repeated cultivation to break up those rhizomes and creeping roots so that you exhaust the reserves. But it's going to be repeated.
That will increase weed pressure though in some cases, won't it, with perennials when you chop them up?
Right, but that's what I'm saying. Usually, and in fact, you wouldn't do it if you've got a crop in there. We actually, when it's really badly infested with Canada thistle, I actually would like to see what we call a summer fallow, which, if you could afford to. Some of our vegetable growers where land is particularly valuable and you're in the mid-Atlantic where, an acre brings you a lot of money, you can't afford to just leave it idle. What you're doing is basically if you've got a bad yellow nutsedge or something like field bindweed infestation, you cultivate every 2 weeks. You cultivate, you allow this to come up, go, or use a herbicide if you wanted to draw out the reserves. But if you would just do that in one season, once or twice, no, that would exacerbate the problem. I would never recommend to a grower to cultivate in a badly infested field with perennials, horse nettle and so forth. And I've seen it, disaster. It's just, you multiply the problem, okay? So that's something to think about. I'm not going to go over this data. You have a similar table. This is just showing you, okay, the duration of wheat presence tolerated, okay, without yield loss. Okay, so this is the critical period of weed competition, okay, and the weed-free requirement for a given number of crops, okay, and different combination of weeds and different locations. Of course, that'll vary, but this gives you an idea, okay. So here's beans. Let's see, red beets, mixed annual weeds in England. A would be this crop. The red beets can tolerate this under these conditions, 4 weeks of these weeds being there without causing yield loss. After that, you've got to get the weeds out. And the weed-free period can be 2 to 4 weeks, okay? And so this gives you an idea, depending on how you start. If you start off with having weed-free period, i.e. the grower is one of those growers that has done a great job, they've cleaned up early in the season, but later on they don't have time and they're wondering, how long do I have to keep this crop weed-free? What it's saying under those conditions, about 2 to 4 weeks, under those weather conditions. That's why I try not to use the weeks, but rather use growing degree days or some other, or the growth stage of the plant, because that will take into account differential weather conditions year to year, okay? So that's a key one, okay? Corn could be this high this year because it was a really, warm spring. In another year, it could be this high, and you can't go on 2 weeks or 4 weeks. You need to go on growth stage. Okay? Again, I would not ask you to regurgitate this, but what it does indicate and give you a sense is how competitive is the crop, or is the weed flora, how competitive are they under those circumstances? Okay? So, that is the critical period. That brings me to the additive design, okay, which is another way that you can measure competition, okay, and so what we just mentioned is very realistic. This is even more realistic. In a sense, this is typically how one determines, well, how many weeds do I need can be in a given unit area, or per foot row, per meter row, such that I'm not going to suffer more than a 5 or 10% yield reduction. So using this method, what you're doing is you basically have the crop planted at a given density, and then what you do, if you're trying to do this experiment, and many folks do it, the growers do it, but unwillingly because they don't necessarily want to see weeds in there. But let's say you're an experiment researcher, and you want to, working with a grower, you want to tell the grower, hey, look, if you've got 1 velvet leaf plant per 3-foot row of soybeans, that's not a problem, even if you leave it throughout the season. You would do that experiment. You would basically, keep the crop is planted at a given density, which is what happens, right? You don't plant corn 30,000 acres in this part of the field, and then 20 in the other, and then 5. It's a given density, okay? And then what happens is you manipulate the density of the weeds within a given unit area. So you might say, okay, what happens to the yield of corn in a growing season if I allow 1 weed per meter square, 2 weeds, 4 weeds of a given species or multiple species? And you then determine the yield loss density relationship, okay? This is what you would typically get, okay? So weed density, you manipulate this as the grower, or you go in there and you pull weeds out and you leave the density that you want to measure. So a grower might measure, what happens if I have 1 velvet leaf, 5, 10, 15, 20, 25? What is the crop yield? How does that respond? This is the general relationship. Early on, low density of weeds, and this, let's assume season-long control, or not control, season-long competition. Okay? Obviously, at lower densities, you may not get a low density. Your yield loss is not going to be that great. Okay? But if you had to describe this relationship, how would you describe what is this relationship between density and yield of a crop? In terms of how would you say this? Should I be worried if I'm a grower and I allow even a little density or low density of weeds in there, generally speaking? I mean, you would do this. I'm just showing you what you would produce if you would carry out this experiment. Okay? That's what the additive design is. You've manipulated weed density, and we've done that. So I could go in a grower's field, and the grower, I'll say, okay, he says, is that okay if I have 2 pigweeds in there? We would do that experiment. Under their conditions over multiple years, we'd come up with a relationship like this. And I tell the grower, how much are you able to tolerate? If he says, I need to be right up here, I'll tell him, one plant is going to be enough. It's going to do you in. This is it. Okay? But what this is showing is look at the decline of low densities. What is that? It's sharp, tremendous decline. What happens afterwards at higher densities, like really high density? It doesn't matter. Once you're past a given stage that you have 100 plants or 200, the damage is done. Okay? You're really below. I mean, it basically flattened out. You're basically starting to get, you're reaching the constant law of constant final yield, but it's your weeds that are taking most of it. You have a lot of weeds. They're all probably very small, but your crop is nowhere to be seen. Okay? So the additive design then, okay, closely parallels what growers typically do, which is plant at one given density the crop, but they manipulate the weeds. So they'll put one weed, two weeds, or three of a specific species. Okay? So if you want to find out, and we do this, even in invasive plant management, where we say, well, how many, stems of Japanese knotweed could be in this spot before it causes main yield reductions in a given rare species, or even makes the species disappear. You can do this. Okay? A different way to look at it, and I don't want to complicate things, but remember the previous graph, okay, was crop yield, okay, weed density. What about if we do now, we plot weed density by, instead of crop yield, percent yield loss, okay, percent yield loss. So here the percent yield loss might be, 10%, 50%, probably up to, 80%. We're going to reverse that. And if you do that, weed scientists have actually come up with a model distribution that fits many of our cropping systems. And it's called the hyperbolic. Okay? I'm not going to go heavy into this, but I just want to show you. When you plot percent yield loss by weed density, this is the relationship. Okay? And you notice that the yield loss early at low densities, just like we saw, whoosh, just exponential growth. And so this you can calculate, and then it basically flattens out. They have done this for many crops, for many weed combinations, and this pattern is borne out. Okay? And you could find out this is a regression. You could look at what the slope is of this, and this is what this is telling you. So YL is percentage yield loss, okay? And you have a number of parameters that you can measure, again, because not all of you have taken statistics or are familiar with regression analysis. But you can actually plug in these values. These are some constants. This, depending on how steep this, slope is, it'll give you an indication of how sensitive that crop is to low densities. The sharper the line, if this thing would have been straight up here, that's telling you this crop cannot tolerate low densities. Even one plant is causing significant reductions. Okay? But generally, this is the pattern. But it'll vary in some species. Some species, you won't have much of a yield loss early on. They'll be more like this. They'll all follow this pattern. It's like the law of constant final yield. Okay? And so the reason I'm saying this is that you can actually have values, calculate what the yield loss, and predict what your yield loss is going to be for a given crop with a given species. But you get this information by carrying out testing experiments that use the additive design. Okay? So the question I have for you is, what is the advantage of additive design? Why would you do it? If I were to ask you, and I have that in your notes. So, why should we do this? What would you answer? What's an advantage? Why am I spending 20 minutes talking about this if it's not a big deal? Steve?
It helps you get the maximum yields and do your management when it's going to count those.
Right. So it gives you an idea of thresholds. How many plants per unit area, per foot row, as I mentioned, can this crop tolerate under the conditions, under these weather patterns, in my field? And we do it in over 3-4 years in a grower's field, and we can predict. Okay. So that's definitely an advantage. So you have an idea. What else, Joe?
Are there like tables or something that you guys have compiled that say in the cucumber field 4 weeks per 10 feet?
Yeah, there's some of that information. I think Cornell recommends in some of their for some of their crops they include some of that information. Okay. The issue there with this is that because weather, so Russ Hahn, who's the crop extension, just to give you an idea, this is nice, but one of the issues here is that he did this work where he was looking at weed density and yield loss in corn over 4 years, different seasons, 4 different seasons. There was not one season that he had basically the same pattern. 1 year, density didn't matter. Didn't care. It had no effect. The line was straight. Okay? Yield loss, was minimal. Just up there, and it's straight. It didn't matter if you had 10 plants, 5 plants, 20 plants. Which is really striking. Other years, just a couple of plants would have caused you a 50% yield reduction. So weather was an important driver. And some of the work we've done in our lab that we've looked at, what becomes even more important is that we know that some weeds, and depending if you have one or a couple of weeds, like for example, velvet leaf, will not be a good competitor if it's a dry spring, dry and cool spring. And we're now able to tell growers, with some of the modeling that we've done, we tell growers, in your situation, if it's a cool, dry spring, velvet leaf is going to be minimally important in your field. If it's a wet, warm spring, no matter if corn likes those conditions as well, velvet leaf will outcompete, will cause significant yield reductions. So it's become a species-specific, okay? And Andy McDonald was here, was a postdoc working in my lab. That's some of the things we've looked at. And so what this is, the reason why this becomes important is that we're able to tell growers early in the season, say, you really need to manage your velvet leaf this year. The conditions are just right for this thing to cause you major yield reduction. So the earlier we can tell growers, the better. But what I'm saying is we learned this through the additive design that, geez, that pattern changes. Okay? So the advantage is that it does give us thresholds, but the disadvantage is that it's not consistent depending on weather. Remember we said, well, it all depends on the weather. Yeah, absolutely. Okay? But it is also a design that's realistic. All growers usually plant, crops are planted at a given density. They're not manipulated, the densities, okay? Like we manipulated the weeds, okay? So those are some of the important factors, okay, that are involved. Yes?
What about for a perennial crop like grapes, for instance? How's that going to change the
That's a good question. In grapes, they tend to be, the problem there tends to be often will be more of perennial weeds would be an issue if you're doing control. And even if you're not doing control, perennials will establish. They're going to be the competitors. I'm trying to remember if this was, most of this was done on annual crops.
I assume.
Yeah, and I'm trying to think of what that relationship, I mean, it's probably density would have an impact, but I bet you that threshold, that tolerance might be a little more, just if they're really well-established grapes. If it's like the first or second year of establishment, then you're going to have major issues. Does anybody have a sense? Megan?
Well, I don't know if it's overall like yield loss, like you're going to have weeds and it's going to relate in a smaller body size, but the weeds that are there will vector over diseases onto the grapes. So that's like, it's just something a completely different perspective. Like you'll see vineyards that are full of weeds, but it's not necessarily like a yield loss because they're competing for resources.
Right, but I've seen
vineyards that are so overrun with weeds that grapes are.
Oh yeah.
I know. I mean,
terrible crop.
But you're right. I have seen
pressure increases in terms of pest pressure increases, but disease pressure not.
Right.
Mostly just because those vineyards are pretty neglected anyway.
Yeah, and but there is that indirect effect that one needs to be aware of, where density plays a role. It's not just a direct competition aspect. I agree, though. I have seen vineyards in the Finger Lakes and the Hudson Valley that, boy, you realize, and the growers knew it. I mean, the vineyard folks, they would say, oh, man, I know that's causing yield. And you would see the grapes, and you would say, oh, man, here's, where they control, they have mulch, or so, but that's a good question. I don't know if any work's been done that. That would be really neat, actually, to get this, but I don't know if anybody's willing to wait to do that. Okay, let's move to the replacement series, okay? Experiment. Remember I said that this is a method to study competition that's most widely used by researchers, okay? And you'll see right away why that's going to be mostly for researchers. And some of you are very practical folks that are coming from on-farm. You'll say, yeah, like the grower would want to do this, okay? And what happens here is the main goal of this is trying to figure out the relative competitiveness of your crop versus a given weed, okay? Or if you have how important is intraspecific competition versus interspecific competition. And you might say, well, of course the grower doesn't care. He's looking at what is going to be their yield loss, okay? That's what's critical to them. But let's say I want to figure out is you know, ragweed more competitive than pigweed, more competitive than my crop, and so forth. One way you could do that, okay, is to use this design, okay? And the way it works is that contrary to the additive design where we keep the crop density, you know, at one level, here we manipulate. The total density stays the same, but the proportions of each of your competitor species, whether it's two weeds or a crop and a weed, changes, okay? So here's the situation. We have species A, species B. You could think of species A as being your crop and species B being your weed, okay? And what you do in one of the treatments, okay, you grow, let's say we decide we're growing this in pots, just for an example. We have 4 plants, okay? That's the total density we're going to use. We've determined that that's the right size for the right number of plants per pot, okay? And I'll give you reasons why we're doing that. But let's say we have 4 plants per pot. In one of the treatments, I'm going to have no crops and 4, let's say we're using velvet leaf, 4 velvet leaf plants, okay? Maximum density is 4, total density. Another treatment, 25%, I'm going to put 1 corn plant, okay, and 3 velvet leaf. So it's a 25-75% ratio, density ratio, okay? You could also think of this as if you're in turf, it's by weight. I'm going to use, 5 grams of Kentucky bluegrass and, 75 grams of, okay, or 75 grams of a competitor species, Poa annua, okay? But let's look at density. In third treatment, I'm going to have 2 plants of corn, 2 plants of velvet leaf. It's a 50-50 split. Do you notice that the total density always stays at 4? Okay? The only thing I'm changing is the proportion of these 2 species. I'm going from 0 to 100%, i.e., 1 corn plant, 2, 3, no corn plants, 1, 2, 3, 4 corn plants. So this is a crop monoculture. It's just the corn, no velvet leaf. This would be the ideal stuff. The reverse is I'm going to have 4 velvet leaf, 3, 2, 1, no velvet leaf. The question you're trying to figure out is, okay, if these guys are equal competitors, what kind of biomass should I get at the 50-50 split based on how well they do in monoculture? So I've got a pot with 4 corn plants. I've got a pot with 1 corn and 3 velvet leaf, 2 corn, 2 velvet leaf, 1 corn, 3 velvet leaf, and no corn and 4 velvet leaf. Okay? So the question I have for you is if the corn and velvet leaf are equal competitors in terms of biomass, okay, what should this give me, this treatment? If I take the 2 velvet leaf plants, I cut them, I dry them, okay, relative to how well they're doing in monoculture, what should I see? They should have half the biomass of what they have when there are 4 of them. Okay? So let's say we do it for corn. Here's corn, 4 plants. I weigh it, let's say they give me 100 grams. Just like you did, we did. We harvest the corn above ground. Let's just focus on above ground. I dry it down. I get 100 grams of corn, of biomass. Now I only have 2 corn plants. Okay? So I've basically replaced 2 corn plants with 2 velvet leaf. If velvet leaf and corn are equal competitors, don't you agree that I should get just 50% of that 100 grams? I should just get 50 grams if they're equal competitors. If they're not equal competitors, I'm either going to get more corn or less corn. Do you see how you can start, based on their proportion in a mixture, I should be able to figure out how competitive these are. And I'll show you this graphically. Okay? So let's say this is corn. This is percentage of corn. Okay? If we have equal competition, when I have 25% of corn, okay, I should get 25% of the yield that I would have had if I had all the corn together. So this takes into account interspecific. Replacing corn, 2 corns with 2 velvet leaf, if they're equal competitors, should not cause me any greater or less biomass. My biomass should decline by just 50% because I only have 2 plants rather than 4. Okay? If I have 50%, I should get 50% of the yield. And you do this. So you plot this diagonal, tells you that there's a direct proportion of the biomass relative to the seeding rate. That's all it's saying. Okay? Fancy stuff, but just for fun. The opposite is true for the yield of B. We plot the yield of B starting here in white. Okay? So no velvet leaf plants, I expect no yield. There's no. If that's the monoculture of. So you notice here it's 100% corn, 0% velvet leaf. I now have 75-25. 3 plants of corn, 1 plant of velvet leaf. My yield should be for the corn, okay, should be about 3/4 or 75% of what I would have had if I had the 4 plants in monoculture. Okay? Because I only have 3 instead of 4 plants. Okay? And so what's going to happen is as I increase my velvet leaf proportion, okay, my corn proportion should be coming down. So when you have these diagonals that are just perfect lines, that's telling you that these 2 species are equal competitors. They're, you know, you can predict their yield based on how well they do in monoculture relative to their proportion. If I only have 1 plant, I should get only 25% of the biomass. Do you think that happens? That doesn't happen that often. Okay? And what we do is when you plot this, or you just add this up, when you add this portion by this portion, you get kind of a straight line. This is basically known as the relative yield total. You have this information. Okay? So how did we get this straight line up here? We added basically the yield of 0 and 100, which is up here. Here's the number. At this mixture, I have 25% corn biomass, 75% velvet leaf biomass. You add the 2 direct proportion. You agree, right, that it should just give you a straight line. I mean, it shouldn't vary much. That is known as the relative yield law. When does this occur? Okay. The reason this stuff occurs is when you have, because of the law of constant, you know, final yield. Which means if you allow your plants to compete long enough in those pots, okay, they're going to compete for the same resource. And then, you know, somebody's going to win out or not, okay? So how is this relevant? You have to be sure that the experiment, you can't do this experiment in 2 weeks and expect to see this relationship. So you have to do a lot of work ahead of time trying to figure out how long do I let my plants grow? How big do the pots have to be? Okay, that's why, can you think of a grower wanting to do this? What grower is going to say, I'm going to be planting 1/4 of my, you know, my field, you know, half of my field with 30% of my corn seeding rate, the other is going to be 50%, the other is 70%. No way. So you see why this is done in small plots, in greenhouses, and small plots in the field. Okay? This is, and then you can calculate, so what this is species A, species B. I've just shown you that, and this is the proportions. Okay? And the relative yield of A to B, you can calculate these. Okay? Relative yield of A in mixture is the yield of A, and you can do this for each of these fractions of these combinations. Okay? When you do that, and your relative yield total, this thing here, if this equals 1, or is closely approximating 1, okay? So you do this experiment with 2 species, and I've done it, and you plot this, and at the end of the day, this is the line. What that is telling you is these 2 species are competing for the same resources. Okay? And I haven't told you at this stage who may be the superior competitor or not, but this is, okay, this is the relationship. They're competing for the same resource. The question that I have for you is if they're competing for the same resource, why isn't one species doing better than the other? You would think that somebody would win out. Why is this not happening? What could be some possible reasons? That you get this kind of nice straight, because I'm telling you, you'll see it sometimes, but it's not going to look like that.
They have symmetrical competitive.
Right. It could be that they're competing, they're using the same resources, but one is going deeper into the soil. Remember we talked about one's competing early in the season for resource, the other later in the season. One is, the root zone is up here, the other's down here. So, and when you put them together, so they could be going after the same resource is being used but at different times, temporally or spatially. Or, as Rob says, they could really be equivalent competitors. It can happen. It's not often, but it can happen. What else could indicate this relationship?
Not enough time.
The experiment has not lasted long enough for them to really fight it out. You cut the experiment off at 3 weeks. You didn't do your homework ahead of time and say, hey, For me to see this, I need to wait 8 weeks. Okay? Or my densities weren't high enough in the kind of pot that I used. I had this, giant 10-gallon pot with 2 little plants that grow this size. They didn't have time. And the size is too large. That can happen. Okay? If this dips, so if this line, think of it dipping down here, is less than 1, it indicates mutual antagonism. Loss of space. How can that happen? Can you think of a situation where you get mutual antagonism? I.e., these species do better when they're alone, okay, than when they're put together. Both of them do worse off when they're put together than when they would be growing alone. Okay? You definitely wouldn't want to use these 2 plants if they're crops in intercropping. You know how we say, well, if you put 2 crops, you get the most out. If this RYT is less than 1, it's saying this is not a good intercropping combination. How can you get that? How can you get antagonism?
Maybe one of them's really good at establishing, for capturing light, but the other's really good at establishing its roots, but both of them rely heavily on both areas.
You could get that. Allelopathy could be another one. They both release a little chemicals that hit the other, and that happens. We have crops, the brassicas can do that, where you go, oh, this is not a good combination. Okay? So you wouldn't want that. If you're into intercropping, or, that is not what we see. Okay? This is what you want to see. Avoidance or symbiosis. Be greater than 1. This thing would go like this. What kind of situation would you get that? Can you think of a crop type combination that would allow you this? Right. You could have, that's exactly it. And that's why most of our intercrops include a legume. Have a legume that provides the nitrogen to the grasses, okay, to a grass, and in fact also reserves some benefits, or there's mycorrhizal connections between the two. So this is, if you're thinking about intercropping, these are the kind of situations you want to see. Is how do I combine them, okay? And is it a good mix? And of course, the kind of things you'll be looking at is, is one of the crops or weed an alternate host of diseases? Kind of indirect effects too, okay? So these are the possible combinations. This is what actually happens, okay? And I just want to show you what this means, okay? This is a situation where both are equal competitors. It would be like our Model 1. These guys are either, as Rob says, they're equal competitors, or the competition hasn't occurred long enough. Don't be fooled by this thing not being a straight line here, because this is not any longer relative yield, it's yield. And of course, you could have corn in terms of biomass could be 200 grams, and if you have, alfalfa, maybe, maximum 100 grams. The yields might be different, but when you put it on relative yield, then that straightens out. The key is that this line is straight. So the relative yield total here, although you might think is this less than 1, it's 1. Okay, it's a straight line. Now let's look at a situation that you get this. You plot this out, okay, and look at these curves. Think of this, of the straight diagonal. This would be the diagonal for A. What is this indicating when you grow A and B? Which one is the superior competitor in this relationship, in this kind of setup? Remember, the straight line tells you that they're equal competitors. Is the concave, convex line above or below the line? So let's look at A. If the diagonal would be here, this would tell you it's an equal competitor. Is A giving you greater biomass, greater performance than you would have expected based on its proportion in the mixture? Yeah, this is what it's doing. It's producing more than you would have expected. It would have been a 50-50 mix. I would have expected a straight line. It should have been here. Why is it above? This thing is doing better when competing with this other crop or weed than with its own. Okay? In contrast, B is not doing well at all. It's performing below what one would have expected based on its proportion. It's 50% of the mixture, but it's not giving you 50% of the biomass, the relative biomass. It's giving you 40%, i.e., it's getting out-competed. Okay? Here's the opposite. A is now the poor competitor. B, okay? So think of the diagonals. Draw diagonals, and that tells you if the curve is above, that's telling you this plant is doing a lot better in mixture than one would have predicted. Okay? And here's that whole situation, antagonism. Okay? Here's the situation where both A and B are not doing well, i.e., This is not a good mixture. They're giving you less than you would have expected. Intercropping, we want to get more out of a given unit area than growing a monoculture. This is not a good thing. And this is, remember we talked about one of the possibilities might be that the two species are allelopathic to each other. Okay? But they're not autoallelopathic. So when you grow, you know, sunflower by itself, it's okay. It's not going to inhibit its own. But boy, you grow with quackgrass will inhibit sunflower. Sunflower inhibits quackgrass if you were growing quackgrass as a favorable crop. This is not, in intercropping systems, this is disaster. We throw the combination out. This is what you want to see in intercropping, i.e. both species do better when grown together than they would do if grown in monoculture. Per unit area of land, you're getting more by putting these two crops together. Okay? This is a symbiosis. That's what this whole legume grass combination is all about. You're limited in land, put this in. Okay? And I'll leave it at that. Let me just summarize. Okay? 2 seconds here. What this replacement series design allows you to do is it allows you to predict, okay, who might be the better competitor over time. Okay? And then when we work with folks like the Nature Conservancy, what they're concerned about is, if I have this invasive plant, how many generations will it take? How competitive is this thing going to be that's going to wipe out one of my rare species? So this method allows you to predict, okay, population or species shifts in a given community. Okay? But it also gives you an idea of who is more competitive. So I could draw, for example, velvet leaf is more competitive than ragweed, is more competitive than redwood pigweed, is more competitive in a given situation. Okay? So those are positive things. What are some of the negative aspects of this type of approach? Hey, is a grower going to have you go in their field and do this? Can I use that quarter acre to put 10% or 20% of your seeding rate for corn or beans? No. Can I use 50%? No. I want the 30,000 plants per acre. Okay? So in terms of practicality, it's not a really practical method to use. You're better off with the additive design or the critical weed peer. But if you want to understand mechanisms of competition, interspecific, this more basic, research, this is a really good method, because it basically says if I replace 2 corn plants with 2 velvet leaf plants, are they behaving the same way as my 2 corn plants? Okay? Or they're going to wipe out, they're going to be out competing my corn. Or no, they're weaker than, actually there's more intraspecific, the corn competes more intensely with its own kind than if I brought a weed in there. That doesn't happen, by the way. It's usually the other way. But you might want to know, let's say I can only control 1 weed out of 2. Which one should I leave? That can happen and say, I just didn't have the right, which one? Should I concentrate on common purslane or should I go after groundsel? Well, by doing these kinds of experiments, say, hey, the groundsel is not as problematic. It's the lettuce or whatever can compete just as easily.